All right, excellent. So let's start with ODP 205. So I posted a new ODP for you. And let's take a look at that. So 205, you're going to be doing things similar to what we did in the previous set of ODPs for PA1. This is the PA2 version of these. So you're working with a struct node, which is defined as you see here. So two pieces, a data field and a next field. Again, the order is still very critical, so you got to have these in the right order for this to work. And you're basically write some code that defines a struct node and write a function named set. Okay, and set, it doesn't return anything, but it takes a pointer to a struct node. So one argument, pointer to a struct node, and what it should do is take the data value of that node, double it, save that in the node, and then set the next field to null, uppercase NULL. So you're modifying a node that's being passed to this function, right? And we're passing not the node itself, but the address of a node. So you're going to get a pointer. You need to look at the thing that it points to, double the data field, set the next field equal to null, right? So it's two assignment statements, and you're done. The test bed is ODP 205.0. Build it into a testable image in the usual way, assess it in the usual way. And so how do we do this? Hold on, I gotta flip my camera again. But it didn't take me as long that time. Oh. Well, now I did it. You don't have to flip your monitor, just stand on your head. It's easier because you don't have cables to deal with. All right, so there's our struct node, and suppose you make your function you've got your set function, which will double the data value and so on. So how do you test this? So from your main program, right? So set up your struct node as usual. Make yourself a node to play with. So we'll say struct node, target, and set target dot data to some interesting value. And set the next field equal to some non-null value, right? And then say set and pass it a pointer to your target. and then print target.data and target.next. And make sure data in this case is 24 and target.next is 0, which is null. And I suggest, you know, testing this pretty extensively. After you do this, change your target.data to some other value, change target next to some other value, call set again, and make sure that, you know, the data still gets doubled and the next still gets set to null. Do that a few times, maybe do it with, you know, not just target, but make another struct node target 2 and try that, right? Really exercise the code. And then when all of that's working, go ahead and you know, link your set.c into the test bed and assess that. So how do we make the set function? Well, you're getting a pointer to your struct node, and so if you want to access the data field, we can do it with that arrow notation. And if you want to access the next field, you can do it with the arrow notation. So, you know, the dash followed by the greater than sign. Those are, you know, the pieces of data that we're interested in. And if you assign a value to this field, it will change the value of this, you know, that field of this structure when you come back from the set function, right? Because you're not passing a node, you're passing the address of a node. And this is basically saying, take the thing at that address, which is, you know, target in this case, and let's do something with the data field. So that's, you know, actually the same address in memory as this thing. So we always say C is pass by value, pass by value, pass by value, right? It's still pass by value, but we're passing a value that's actually a reference. And so we're mimicking pass by reference, which lets us change the value of an argument that's been given to us, just like scanf can change the value of an integer that you pass to it, provided you pass, you know, ampersand integer, the address of it. So see if that gets you success in setting the null next field to null. And remember, in C, it's uppercase N-U-L-L. It's predefined. Achieved success. Excellent. Very good. All right, so questions on the ODP. All right, on to PA2. So PA2 should be accessible on Canvas. Now let's see what that's all about. All right, this should look very familiar to you. Okay, you're going to implement a linked list, but instead of using an array, you're using dynamic memory. This is really the key difference from PA1. So your node structure is a little different, right? Your next field is not an int, it's a pointer to a struct node. There's no valid field, right? The system's taking care of valid for us. There's a sentinel node. And in your main program, you should declare the sentinel node as struct node star. And you don't have to call it list, but I'm going to call it list in our discussion of it today. But it can be any name that you want, but it's a pointer to a struct node. Okay? Don't make your sentinel just a struct node. Make it a pointer to a struct node. The reason being that init is going to return the address of a new sentinel node. All right? And I put a note here. This is the one function whose prototype changes from PA1. Right? PA1 init was a void function, I believe. PA2, it returns a pointer to a struct node. So when you write your main program, what do? You set up something like you know, this is your main for PA2. So you set up something like struct node. And there's my sentinel. And to create the empty list, I'm going to do something like that. Call the init function, the value it returns, set sent equal to that. And now sentinel should be, referring to a box with a next field equal to null. This is not ODP 205, by the way. We're doing something slightly different in the ODP. But if you can do the ODP, you can make your init function. But the doubling of the data is just something extra to do. All right, your add function takes a pointer to a struct node and takes an integer, and it tries to add that integer into the struct node. Right? The list should always be sorted. The function returns 1 if successful, 0 if there's no memory left. Which means that when you tried to get a node, you got null back from that function call. Print just takes a pointer to a struct node, prints out the elements of the list, all on one line, right? In sorted order as usual. Delete takes a number and removes it from the list. It cannot fail because you should only call this if your number is actually contained in the list. So it's a void function again. Search searches the list for a number and returns 1 if it's found, 0 if it's not. All right. What else do we need to say in here? To add a number to the list, create a new node, search the list for the proper point to insert, which is the first node greater than what you're inserting. Adjust the prior nodes next to point to the new, adjust the new nodes next to point to the one that comes after it, and so on. All right, you should use malloc to get the address of a new node and free to release the node. So these take the place of get node and release node. When you're adding a node, first thing you want to do is create a new node in memory somewhere, call malloc. Call it with size of struct node, and that will give you a chunk of memory that you can use as your node. When you delete, adjust the prior pointer to point to the thing after the node you're deleting. When you're completely done with a node, when you're not going to do anything else with it, then go ahead and call free with the pointer to that node that you're done with, and that returns it. You also need to use the free function at the end of the program, because we don't want any memory leaks, right? We need to make sure that when our program is completely done, any memory we've allocated has been freed. Now, when we delete a node, it's pretty easy to free the memory because we're used to calling release node. But we have an extra requirement here, which is at the end, when you say exit, if you have a linked list with 20 things in it, you need to release all of those nodes. Okay, we'll talk about how to do that. Your main program looks exactly like your previous main program. Print a prompt, greater than sign, followed by a space, wait for the user to type something, followed by an enter. Legal commands, I space number, P, S space number, D space number, or X. Right? X should cause the program to exit after freeing all allocated memory. Anything else, give a synopsis of legal commands. So that's the same interface that you're used to. All right, deliverables are pretty much exactly the same. So all the above routines, main program, plenty of commenting, okay? In the beginning, right, before each function, I want a comment block which says the name of the function, right? So clearly, indicate the name, what the function does, and then also describe every input to the function and the return value if there is one. And I suggest doing this as kind of like, inputs, list. This is a struct node star, it's the linked list. Number, this is an integer, this is the value that we're trying to insert into the linked list. Make it like a bulleted list or something. So that somebody can easily find, what's this variable Fred, right? Oh, that's the name of the linked list. Okay, cool. Alright, this should be explained in a set of comments appearing immediately before the function definition. Code should be commented throughout, and I did put a note in here. Your main program should also be commented throughout the code of the main program. Comment block in the beginning as usual, and a make file for creating an executable image. This should go into a GitLab repo named linklist2. Make sure I have reporter access. And on Canvas, I posted a note. You have about 24 hours if you want to do a test push to your repo. So make yourself a linklist2 repo, push it over to GitLab, put a README in there, add my name as a reporter, and then send me an email, right, to my direct email, nmaciasclark.edu, before tomorrow at noon. Okay, if you do that, I will try to download your repo and I'll let you know if it's there or not. Wish we had that kind of detail on PA1 regarding commenting. You did have this detail on PA1. The only thing that I've added here was making sure you comment the main program, which I didn't take off points for if you didn't do, and making sure you list all of the inputs and outputs, which I did mention on the previous one, but I didn't grade as harshly as I had planned to. But PA1 also said, you know, comment block in front of each function, comment block in the beginning of main, comments throughout your code, and things like that. And that's going to be, you know, the case going forward. We're going to want all of that stuff. All right, so grading, mostly the same as last time. If I can't download your code by the deadline, it's automatic 20 points off. You have 24 hours to correct it. If I can't compile it or I can't run, that's at least 40 points off. If you're not, you know, if you're not doing the program right, that's 0 points. So you've got to be using a linked list of struct nodes, dynamically allocated in memory, and so on and so forth. So specific points: proper make file, meaning selective compilation, which everybody did, which was great, 5%. Each of your 5 basic functions is worth 10% now: init, print, add, search, delete. Main program is worth 10%. If when I run valgrind on your program, I get no memory leaks, no errors, and no warnings, that's 10%. Right? If I get a single warning, 10% off. So make sure you deal with those warnings, okay, and ask about them. They're there for a purpose. They're not just, you know, I feel kind of funny about this code. There's a problem with your code if valgrind is giving you warnings. Even if your code looks like it's running correctly, there's a problem somewhere, right? So take advantage of using valgrind to make sure that your code is squeaky clean. I would like to see no warnings when I compile your program using just the default GCC command on the Linux server. That's worth 5%. So if you forget to include something, if you should be using one type of variable and you're using another type, anything like that, right? 5% if you avoid all of those warnings, and obviously no compile errors. Otherwise, it's not compilable. That's the 40 point. Commenting before each function that clearly explains the function in detail is described above, 5. Main program comment block, 5. Comments throughout the code, including in the main program, 5. And then consistent indenting, some kind of coding style, that's the last 5%. And yes, someone pointed out in chat, if you write code with memory leaks, people won't want to use your software, or they'll use it and they'll say nasty things about it to other people. All right, so questions about that? If I graded on Thursday, it would not be ignore warning Thursday, but I'll probably grade it on Friday. So, yeah, ignore typos Thursday. Alright, let me take a look at something. Alright, Questions about PA2, other than how to do it, which we're going to work on next. So let's do a week from Friday. I probably will not be giving you an extension on this one. Once you understand the idea of using a pointer as a pointer, right? And you get some experience with you know, using the arrow notation instead of this notation. That takes some getting used to, but once you get through that, this assignment is really fast, right? If you have PA1 working, you can almost, like I said, just do some global substitutions and turn it into PA2. Now don't do that, right? But you can start with PA1 and go through and change it to use this, you know, dynamic memory approach, and you'll start seeing that you're doing the same things over and over and over again, right? And I think that helps, you know, sort of cement the ideas of how this relates to, you know, pointing to things in memory just like we point to things in an array. Question in chat: when we call malloc, how will we know what memory location it gives us? That's the return value from malloc. So if you say something like struct node blah, malloc, and don't put a magic number, use size of, and put in a type, not a variable. And you want a struct node, not a struct node star, right? The value of this will be some location in memory that malloc decided was available for your use and your use alone. So that's a memory address in there, right? You need to check to see if it came back null, and if it did, you're out of memory. And then somewhere when you're done, you need to call free with that same address. Yeah, I think malloc is just memory allocation, but you know, knowing Unix, it could be something really strange. But that's probably all it is. Allocate and free dynamic memory. So it could be fdum or something like that. It does sound like a Mesopotamian god. All right, good stuff. So will we have a variable name for each node? No, this is the magic of dynamic memory. So how do we avoid having a zillion variables as we build our list? This is not what you're going to do, right? But let me just show you some code. So sentinel equals malloc, you know, whatever, which makes a sentinel node. And then new equals malloc, which makes a new node. And sentinel next equals new. So this points over there. Well, at this point, I can change the value of my variable new, right? I could say new equals malloc. And now this is no longer new. New is some other block of memory, but this block still exists. I don't have a variable that refers to it, right? I changed the variable new to point to this new block when I said new equals malloc again. But I haven't lost this block. It's being pointed to by the sentinel. And if I want to squeeze this block in between those two, I could do the following. new next equals sentinel next, which says look at what the sentinel is pointing to, have new point to that, and then sentinel next equals new, which changes this to point here. I've got a list of 3 things now. And if I call malloc again, this is no longer new. New is now some totally different block, maybe in some totally different area of memory, but I still have all 3 nodes here. The only variable that I need to make sure I keep track of is my first node, my sentinel. If I change that, if I change sent equal to malloc, this list is lost. And that'll show up in Valgrind when I exit. But as long as I keep my handle to the whole list, my address of that first node, I can follow the links and get to any node that I want. Let's see. Oh, we got plenty of time. So all the other nodes besides the Sentinel and new are nameless. Yeah, pretty much. They you know, are pointed to by someone, but we don't have a variable anymore that refers to them. And when we call our add function, right, the add function is going to make a new node, set up the pointers, and so on. When we return from the add function, you know, those local variables inside add that were referring to new and previous and so on, those are gone too. Right, so it's a little tenuous feeling sometimes, but you know, if we've got the Sentinel, we can follow that to get to everything. Wow, did I not make a struct node at all? Hey, I did. Okay. So let's continue some sample code. So here's my struct node. And we've got 3 nodes here: Sentinel, first, and last. So Sentinel, first, and last. Sentinel points to first, first points to last. Okay, so all right, so this is bogus code here. Okay. We really want a pointer to the Sentinel when we're doing this, but what I want to do here is look at what a print function might look like. Okay, so I'm just going to build a linked list by hand here by creating, you know, 3 nodes, Sentinel, first, and last. And I'm going to call my print function by passing the address of Sentinel with an ampersand in front. We're not going to have to do that normally because Sentinel is going to be a pointer. But I don't want to write, you know, too much of PA2 for you. I want you to be able to do that yourselves. So So I'm deliberately making this kind of bogus, right? So this was code from yesterday. We built a linked list that starts with a sentinel, points to a node with 10, points to a node with 20, and 20 is the last node in the list. And I want to develop a print function, okay? And I'm going to call it by passing the address of sentinel. So let's prototype print. So that takes a pointer to a struct node. And so here's our print function itself. Takes a pointer to the sentinel. So what could we do? So I'm just going to move down the list and print out what we've got in our nodes. And remember, sentinel is a pointer, so we can't say sentinel.data. It's got to be this funny notation. So we'll print out the data, and then we'll print out the next field. And then let's move down the list. Let's set sentinel equal to sentinel next. And let's just do that 3 times. So this is obviously not your finished print function, but this is sample code. All right, so we're building a list by hand, and our list looks like this. So sentinel, 2 data nodes. And I'm going to call print with the address of the sentinel. So my print function right now is going to print out the data next field in that sentinel, and then change sentinel to be what it points to, which is the 10 node. Print out the data next. Change sentinel to what that points to, which will be the 20 node. Print out the data next. And I don't need to do this last movement. Nice. Good lyrics. And hopefully we don't end up feeling like that when we're working on linked lists, where we have to set our horse free and so on. All right, let's run this thing and see what happens. All right. So our sentinel had a data value of 42, a next value of this. At this address, we found a data value of 10 and a next value of this. And at that address, we found a data value of 20 and a next value, which came out as nil. Now I'm printing these pointers with a %p. And %p is something printf understands that says, hey, this is a pointer. So for us, it'll treat it as a 64-bit number, and if it ends up being equal to 0, it'll print the word nil in parentheses. So we get this nice, indication like that. And if I run this again, I get different output, right? My data fields are the same, but my sentinel pointed to a totally different address. Right? This was 7FFC8, this is 7FFEC. It's like way off. And if I run it again, it'll point somewhere totally different, D6. This actually helps with security of code, right? Not always having the same locations being used makes it harder to predict where another running program might be storing information in dynamic memory. I don't know if that's the case here, but that is a security enhancement you find in some systems. So this can make debugging interesting, right? Generally, writing down addresses works great while you're debugging a particular run of your program. If you exit GDB and go back in, good chance you'll get different addresses next time you call malloc. All right. Now, if we didn't know that there were exactly 2 nodes after the sentinel, right? What will we do here? Well, we put this thing in a loop. And so it still works until we segfault, right? So we got our 3 data nodes, we got our 3 pointers, but at this point where next was nil, what's the code do? Well, it sets sentinel equal to sentinel next. So now sentinel is null, and the next time through it tries to print the data field of a structure that's supposed to begin at location null, and that doesn't exist, and that's where we're getting our segfault from. So what's the sort of most likely while condition that we could use here to avoid a segfault? Make sure we print all the nodes and then stop just in time. And then I'll tell you about core dumped. So for this, the way I've written it, right, it's probably where sent is not equal to null. But it's a little quirky because I'm printing the sentinel node too, and in PA2 we don't want to print the sentinel node. But if we didn't worry about the sentinel, if we just saw a chain of nodes, yeah, this is probably the right condition. We don't want to stop when sentinel next is not null, because even if sentinel next is null, we might still want to print the data in the current node. So if we do this while sentinel next is not null, then this works exactly right. All right, what is core dumped? I don't know if some of you have possibly never been in the STEM building, because we've been locked down for almost a year now. But if you've been in the STEM building, there's a display case outside the collaboratorium. You see it when you're walking down from 155, 153 towards the collaboratorium, the place where you have to make the left turn. There's a display case there, and it's got various parts and EDBOTs for 270 and so on. And there's a little display on the right side, about halfway up. It's an old style memory. It's a board I bought off of eBay from a Soviet clone of a machine called a PDP-8. And if you look closely at it, it's fascinating. It's a bunch of little tiny ferrite beads with holes in the middle, laid out in a 2-dimensional array, with wires running through them in 2 directions, and it's woven together. And these little beads, right, they're ferrite. They're like little metal donuts, and they can become magnetized. And by running current down, a pair of wires, they will intersect in exactly one spot, and so you can change the polarization of the magnetic field on one of these dots. That's how memory was implemented, right? And it was non-volatile memory, so the main memory of your program wouldn't go away when you powered it off. And so these were called magnetic cores, and this whole thing was called a core memory. And so when you get this message saying core dumped, right, what it meant, well, in the old days, when you got a segfault, it would read the contents of memory and it would write it out to a file. And we were talking where memory was like 64K maybe, so not that huge. So you'd get an error. A complete dump of everything in memory would be written to a file, and now you could go in with GDB and you could set up the system exactly as it was when the error occurred. You could see the values of all your variables. You could see, what was stored in memory and so on and so forth, and that would help you debug. This doesn't happen anymore, but it used to be when you got that, if you looked in your directory, there'd be a file named core, and that would be a copy of the main memory, which, isn't core memory anymore, but it's still called core. And sometimes you encounter people and they talk about core dumping on you, like when you've had a really bad day and you've got to just kind of like unload everything that's happened to you, right? I know people who call that core dumping, so that's the thing. Yeah, I miss the STEM building. I actually wonder if it's still there sometimes, because I wonder if my office is still there, and I've still got a cell matrix demo running in the window, and Albert Einstein is still standing in the corner, and so yeah, it's been a while. Yes, you would see me walking with some lady. That's my fiance now. She would come and visit me, and we'd have coffee before I had to teach, and she had to leave. Yeah, thanks. We don't have a date because, COVID. But yeah, we're officially engaged, so that's pretty cool. All right. So yeah, core dumping is the nerd's version of venting. All right. This is the essence of your print function, and it's the essence of what you do for most of your functions for PA2, right? Now we don't want to use the Sentinel node, right? That's just a handle. So what can we put in here to skip over the Sentinel node? Give me a line of code. There, I put in the comment for you. Well, a for loop might get us over a bunch of things, but our goal right here is just to, instead of printing this, followed by 10 and followed by 20, let's start by printing this as the first node. So we use the Sentinel as, our handle to the list, but we want to skip the first print. We want to just start with the 10. Yeah, so let's just use Sentinel next as our starting Sentinel. And then, as long as that's not null, print out the data value, print out the next field just for fun, and then move on to the next node. Go back and do it again. Just keep doing this. So there's a good print function. And some of you may be weirded out that I'm using Sentinel here and I'm changing it and so on and so forth. Remember, this is a local variable. Now, if I didn't want to do this, right, I could do something like this. we've been calling this thing current, and I could start off with current being the sentinel, the thing the sentinel node points to, and while current is not null, print current data, print current next, and then set current equal to current next. And that's closer to what we've been doing, you know, in other functions. But it's exactly the same thing. I just changed the name of a variable, right? But if you don't like changing arguments, right, this is one way to get around that. And if I wanted to keep the previous node, right, I'd make a struct node star previous, and you know, I could initialize that to the sentinel, initialize current to the sentinel next, and then do my pair of pointer thing that I've done so many times before in PA1. So the algorithms for PA2, right, for add, search, delete, they're exactly the same. Right? Search, you basically do what you're doing with a print, but instead of printing, you're just comparing the thing you're searching for to the current node's data. And if you find it, return 1. If you get to the end and you haven't returned, the data wasn't in there, return a 0. Delete, you move through, but you keep a pair of pointers. Keep the previous and the current. When you find the node that you want to delete in current, then set the previous to point to the thing that current points to. And then add, same thing, when you get to a place where current is bigger than what you're inserting. Make a new node, have previous point to the new node, have the new node point to current. And you're all set. Yep, so for PA2, the limit on the number of nodes is just how much memory the system can dredge up. And you're really not going to run out of memory. Something very unusual is happening if that's the case. But it's still, you know, important to check the return from malloc and make sure that it's not null. Just so that if you run out of memory, you don't start, you know, stepping on strange things and corrupting your list. But if you run out of memory from malloc, your print statement's probably not even going to work. Your system's probably on the way down. But check it anyway. Yeah, it's pretty hard to test the case where you run out of memory, so I wouldn't even try. Because like I say, if you run out of memory, there's a good chance the system's going to panic and you're going to lose the system anyway. If I run valgrind on this, right, tells me heap summary and use at exit 0 bytes 0 blocks. I never did any mallocs in here. Right, I didn't do any dynamic allocations. I constructed my list in this bogus way, right, by hand, by just making 3 struct nodes and setting them up to link them together. But if I had, you know, created these with a malloc statement, then when I run valgrind, if I didn't free these, it would tell me, hey, you've got, you know, memory leaks. So tomorrow we'll talk about how to free all the memory when your program exits, because that's a fundamentally new piece. But you basically do it the same way that you print. Start with the sentinel, move forward, but basically as you're walking down the list, you're freeing the nodes behind you. Right, so you've laid down a trail of stones. If you want to get rid of the trail but still not get your feet dirty, what do? You walk on one stone, you walk to the next stone, pick up the one behind you, walk to the next stone, pick up the one behind you. When you're done, you've picked up all the stones. That's basically the free algorithm. So we'll spec that out tomorrow. Go ahead and work on the ODP. Think about PA2, start coding it if you like, and I will see you tomorrow. All right, thanks.